Let's get started. Good morning. Welcome to the third session of Introduction to Photonics. Today's session is going to be slightly different in the sense that we've dealt with a little bit of theory so far. So let's try to work out some practical problems. Okay, let's try to design something, for example. So we already designed an endoscope earlier this week, and so we can try to see if there are other things we could design based on the principles that we have learned so far. So what did we learn so far? We learned to identify that there are different approaches to photonics, the science of light. Essentially, we said the basic approach is considering that light travels in straight lines, which gives us ray optics. And then what we have learned in the last couple of lectures is that the ray optics have some limitations in terms of describing properties of light. So especially when we have light encountering feature sizes which are comparable to the wavelength of light, we are having to invoke the wave property of light. So the last lecture we saw how a particular light wave can have a wavelength, can have phase, and based on those properties, how can we explain certain physical events that are happening, right? The physical processes that are happening. And we took the example of Young's double slit experiment to show the process of interference, constructive and destructive interference, which obviously couldn't be described using just ray optics, right? So what we're going to do today is take a couple of examples, one related to just ray optics and another related to wave optics, in line with the kind of discussion that we have been having this week, and let's see how we can work through that, whether we have enough knowledge to work out problems like this. Okay, so let me just take the first example. Example 1 is about dispersion in a prism. Okay, so how do we get dispersion in a prism? So what is dispersion? Scattering of light is an answer that's given, and that's not entirely correct. Scattering is another phenomena which we have not really dealt with so far. We'll reserve that for some other time. Is there a better definition of what dispersion means? Spreading of pulses. Well, that's again something that we have not talked about. Maybe we will come back to that a little later, but that's the effect. There is a more fundamental physical process which can represent dispersion. So yeah, spreading of colors, basically discriminating different colors. So essentially the material, like I said yesterday, the material, when light wave goes through a material, the material responds differently for different colors. Okay, if it responds differently for different colors, then you get an effect wherein you are spreading all these colors. You are able to spatially separate out all these colors. Okay, so that's what we're going to check first. And of course, we said dispersion is in a prism can explain separating colors, and that can possibly explain how a rainbow is formed. Okay, I will come back and requalify that statement a little later, but let's just say that each of those water drops can be modeled as a prism. Okay. So specifically modeled as a thin prism. So let me just draw this prism over here, and what we have now is a ray of light that's coming in. Maybe I can use a different color. Coming in and a ray of light going out from this prism. And of course, what is happening is you have refraction happening in this case, and it's going to go through that. We are considering a transparent medium, so it's going to go through that. And what we are asked is to figure out, if it had gone straight, it would have ended up there, but instead it got deflected over here. So what we need to figure out is this angle. Let me just represent that as delta. Okay. So we want to figure out delta, and specifically we want to know if delta is different for different colors, right. Only if it's different for different colors, then we can say, all these different colors are spreading out and then it's giving you a rainbow, right. So to do that, what do we have to define? We have to define the refractive index of the material. Let's say, we are modeling a water droplet, okay. So water has a refractive index for blue color. It exhibits a refractive index of approximately 1.34, and for red color it exhibits a refractive index of 1.33, okay, and other colors in between take values between 1.34 and 1.33, okay. So if we have this situation, can we find out delta, right, that is the angular deviation, okay, as a function of these two colors? Can we see if those two colors separate out? How much do they separate out? To do that, of course, we do need some parameters. Let's say this prism has an apex angle A, okay. So if it has an apex angle A, then the question is, based on that apex angle, can we express that delta, that is the angular deviation, as a function of that apex angle as well as this refractive index, okay. So how do we go about solving that problem? Now to solve that problem, clearly we need to define a few things. First of all, we need to define this normal over here so that we can apply Snell's law at this interface, and we need to define the normal over here, right. So we can apply Snell's law at that other interface, and these two normals, we understand that that intersects each other, and that makes an angle, let us say alpha, let us call that angle alpha, okay. And we also know that this is incident at an angle, let us say theta 1, it goes out at an angle theta 2, it is incident on this interface with an angle theta 3, and it goes out with an angle theta 4, okay. And let us for simplicity consider this prism as a thin prism. So what is the effect of that? if it is a thin prism, then all these angles that we are considering theta 1, theta 2, theta 3, theta 4 are fairly small angles. Okay. So, then you can apply the paraxial approximation. So, what is the advantage of using the paraxial approximation? Of course, it makes our calculation simpler. So, you have n1 theta 1 equal to n2 theta 2, okay. So, that Snell's law becomes easier to compute, okay. So, first of all, we understand that when we consider that trapezium over there, what we find is it has got these angles A and alpha, and it also got these angles over here. What are those angles? At this point over here and this point over here. Those are by definition, these are at right angles, right, because those are normals that we have considered. So, those are already 90 degrees. So, the total internal angles have to be equal to 360. So, you have 290 degrees. So, you take that out. So, you can basically write that alpha plus A has got to be equal to 180 degrees, right. Now, if I consider instead of that triangle, if I consider this triangle, okay, then what I can say as far as this triangle is concerned is theta 2 plus theta 3 plus plus alpha equals to 180 degrees. So, alpha is common for both of these expressions. So, based on this, what you can say is that A can be expressed as theta 2 plus theta 3, right. So, that is one thing, and then if we go on to express these angles over here as let us say this is we represent as beta, and if we extend this ray over here, let us call that angle as gamma, okay. So, if we represent these two angles as beta and gamma, then what you can write this as is you get this expression for delta. So, delta becomes equal to beta, this overall angle delta is equal to beta, and then what is the additional part to that? If you just extend this on the other side, the other angle would also have to be would be gamma, right. If I extend this red ray going across that prism, right, if the other side will be gamma. So, delta will be equal to beta plus gamma. Do you see that? Right. So, if this if the internal angle I have expressed as gamma, if I look on the other side of the interface, if I just stretch that red ray across, then that angle would also have to be gamma, okay. So, you have delta equals to beta plus gamma, but beta itself can be expressed in terms of theta 1 and theta 2, right. So, what is beta in terms of theta 1 and theta 2? Beta will be equal to theta 1 minus theta 2, right. And similarly, if you are expressing gamma, what is gamma? Theta 4 minus theta 3, okay, right. So, this can be written as theta 1 plus theta 4 minus of theta 2 plus theta 3, but theta 2 plus theta 3 is what? A, right. So you basically get an expression that is connecting delta to A, which is the apex angle of the prism that we are considering. So now we can apply Snell's law at the interface. So I can write theta 1 as what? Let us say we are going from air to a medium, in this case we say water, right, with the refractive index n, okay. So what is the corresponding theta 1 is can be written as n times theta 2, right. So similarly theta 4 can be written as n times theta 3, right, minus A, and we know theta 2 plus theta, so n is a common term, so then you take n outside, theta 2 plus theta 3, which is equal to A. So you get NA minus A, or you can just write this as n minus 1 multiplied by A, okay. So just some basic geometrical principles, and then we apply Snell's law and we got this expression that delta is now n minus 1 multiplied by A, which is of course an approximate expression. What is the approximation that we have taken? Paraxial approximation, right. So if you want to extend this to any arbitrary angle of incidence and thick prism and all of that, then you just go ahead and use that sine theta wherever necessary, and then you get a slightly more complicated or complex sort of expression, but nevertheless it gives you some sense of what you can expect, okay. Now does this convey the thought that we are going to have dispersion in the prism? When you look at that expression, what part of that expression tells you that there is going to be dispersion or separation of colors? That angle of deviation, yes, but what specifically gives you different angle of deviation for different colors? The refractive index. So delta is dependent on the refractive index. So if I substitute these values for different colors, then I get a different theta, angle of deviation. So let us just do that, right. So let us say delta for red color, let us say A equal to 10 degrees, okay. So delta for red color is going to be 1.33 minus 1 multiplied by 10 degrees. So that is going to give you 3.3 degrees, okay. And delta blue is 1.34 minus 10 degrees, that is 3.4 degrees, okay. So effectively between the two there is only a 0.1 degree a change in the angular deviation, which seems fairly small, right. Now, of course, if you project that over a long distance, so that can actually look like a fairly large or significantly large spatial separation between the colors. But that's the kind of effect we are talking about, that essentially shows that there is going to be dispersion. So, if I were to draw this blue light also in the same graph, what I would see is, because of this higher dispersion, it is going to take a slightly different path in a slightly different deviation. Okay, I am just exaggerating that for effect over here, but you can actually see what is the dispersion you are going to see, or you are going to have when you consider a prism like this. Okay, now it turns out this is not how you explain a rainbow happening. Okay, so to give you a feel for that, what you say is the rainbow happens because your water droplet is spherical in shape, slightly spherical in shape, and so this sunlight actually goes through this, undergoes total internal reflection, comes out and scatters out this way, right. And so we are here seeing this, this light, and we see a rainbow, and specifically if you, but this principle applies in a similar way, right, because you say, okay, different colors are going to go through different angles of refraction within this water droplet, and the separation is going to be very similar. Okay, so you see that red and blue light and all the other colors separate out nicely, and that's how you see a rainbow. Okay, but that just to quantify dispersion. Of course, what happens in the actual rainbow situation is that it's not only that we are looking at this from a distance, but also the fact that this scattered or this dispersed light can go through multiple successive dispersion in other droplets, right. So, you can essentially get an effect that is magnified in terms of dispersion. I do want to let you know that this is a fairly powerful concept to utilize. Of course, you can use this as a spectrometer. For example, I think when Sir C.V. Raman essentially looked at the separation of colors, used a spectrometer, right, to say that, okay, there is actually Raman scattering happening, and that gives a different color from what was incident on the medium, and that spectrometer could be something like this. It could be based on a prism which separates out the colors, and what you do is you put a slit over here if you want to see a particular color. So, if you move that slit, you can separate out different colors. Of course, in modern day, what we do is we actually put a CCD array over here, right. If you put a CCD array, each pixel is actually picking up a different color. So, modern day spectrometers could be actually looking at differentiating colors by using some dispersing element. It could be a prism, or it could actually be a grating also, which we had not talked about, but the depth of that corrugations in the surface is actually periodic, and that can give a similar effect. If you get a chance, maybe we will go back and look at that next week, but that can also separate out colors in a in this way. So, you could have a grating based spectrometer, or you could have a prism based spectrometer. Grating based spectrometers are typically more preferred because it can give you more separation of the colors, and we'll probably come back and look at why that's the case, okay, at a later point. But this prism can also help in, somebody was talking about dispersion of pulses. So you can imagine that when you are sending a pulse of light which consists of multiple colors through a medium, and if the medium responds in a different way to each of those colors, meaning it actually gives a different refractive index, okay, for each of those colors, then the speed at which light is propagating. So, speed at which light is propagating in vacuum or free space, you can represent it as c, but when you are talking about speed at which light is propagating within a medium, you represent it as c over n, right. So, this is actually the velocity of light within a medium. So, you can imagine that when light is going through this medium and the medium has dispersion, meaning the refractive index is actually a function of wavelength, okay, different colors are traveling at different speeds essentially. So, if you have a pulse of light, if you have a very narrow pulse of light, okay, if you look in the Fourier domain, what does that represent? It represents a spread in frequency, right, or spread in wavelengths. So, different wavelengths are now traveling in different colors. So, your pulse essentially gets spread out, right. You started with a very narrow pulse, but because of the response of the medium, you are starting to have a spread, right, just because all these different colors spread out, okay. And that is actually a major problem in optical communications. You can imagine this, it is going through a glass medium, and that glass medium actually provides different refractive index for different colors. So, if you have multiple colors going through that fiber, and we are talking about propagation over hundreds of kilometers of fiber, okay, then all these colors separate out, and the pulse essentially you started with a narrow pulse, right, but after going through this optical fiber, it actually becomes a broad pulse, and all these colors essentially separate out, right, and they arrive at different times after they go through this fiber, okay. So, if you have dispersion like this, you are essentially saying that, okay, in this case C over n, so n is actually larger for shorter wavelengths, okay. So, shorter wavelengths travel slower compared to longer wavelengths, but nevertheless, so when you are looking at this pulse spread over here, you have blue over here and then red over here and all the other colors in between. Now, can you do something about this pulse spreading? Can you actually recompress it back to the original pulse? Yes, because all these colors are nicely sequenced. So, if you find an element that can delay the red with respect to the blue, then you can actually get the pulse back, okay, and that is actually a process called dispersion compensation, okay. So, you could possibly use a prism based technique to do dispersion compensation, okay. So, we are talking about some fairly advanced concepts, but if you know the fundamentals, you can actually dare to dream of, taking care of those things. And it's amazing how, however far you go, however more advanced you go in photonics, you always have to come back to the fundamentals, and you start thinking about some fundamental concept and you think, hey, that's a cool way of taking care of this problem that we are finding in this advanced system. Okay, so you'll find that as you mature in photonics, as you take more and more advanced courses in photonics, you'll find that you always come back and revisit some of these fundamentals, and there's value in doing that. Let's take another example, and curiously enough, this example is also going to be based on the color of light, separation of color of light. Okay. For this, I want to go back and see what we did yesterday. So, this is what we did yesterday in the last lecture. You had this Young's double slit experiment, and we got to the point of realizing that you have constructive and destructive interference happening due to this double slit, which each of those slits were size comparable to the wavelength. Okay. And interestingly, we said, did we work out that final thing? No, we did not. So, okay, maybe this is an opportunity to do that. If you see this interference pattern closely, if you see what's happening over here, right? So, why do we have such a maxima here? This is actually looking at the intensity of light as a function of position. We have a maxima there. Why do we have a maxima over there? Because this wave and this wave have come together there, and because the path length difference between them, PLD we call that path length difference is, it's providing a phase difference between them, which is an integral multiple of 2 pi, right. So, how does that work out? Because what we talked about, and maybe I did not explicitly mention that, when we are talking about phi 1 minus phi 2, that is basically given by 2 pi over lambda n into let us say this is L1 and this is L2. Did I switch the notations a little bit? Maybe I did. So, we call this 1 and this 2. So, L1 and L2. So, this is basically n L1 minus 2 pi over lambda n times L2, okay, and n is a common term. So, this you can write as 2 pi over lambda n into L1 minus L2, and this L1 minus L2 is what we are calling as the path length difference, okay. So, if you work out the path length difference over here, we will find that that is actually dependent on the wavelength, okay. So, or the path length difference required to get that constructive interference is actually a function of the wavelength. So, let me just, since this place is already quite busy, so let me just take this over to this other document and then we will look at this. The point here is, what we are trying to examine is, can you discriminate different colors using Young's double slit apparatus. Okay. Can you discriminate different colors using Young's double slit apparatus? So, we are going to redraw this apparatus here, and we are going to say once again this is a light wave that is incident on this, and that is actually setting up secondary waves over here which are interfering, and at a distant observation point, you get to see a maxima over here and a maxima over there, and similarly a maxima over there, and so on. And so on, right. So, what we are interested in is where does this first maxima happen? Let us say that is that we denote that as x1. Let us say we are told that this distance d, let us call this, is given as 1.5 meters, and this distance, which we call as small d, we are told that corresponds to 0.8 millimeters. Okay. So, we want to see if we can discriminate different colors. In other words, let us say we want to see if we can separate out red color from orange color. Okay. So, let us say lambda of red is 650 nanometers, and lambda, the wavelength corresponding to orange, is let us say 600 nanometers. Okay. Well, it turned out to be yellow, but does not matter. Okay. Let us say, let us see if we can separate out these two colors. So, if we work out that path length difference that I mentioned over here, so you can drop a perpendicular from here, just put this in dotted lines, and then this path length difference, can I express that path length difference in terms of d? Okay. To do that, what we need to consider is actually the angle that it makes with the these two beams approximately make with the optical axis. Let me call that as theta. Okay. So, if this is theta, then what I am doing over here is I am just changing the axis, because this is also a perpendicular. So, I am changing this axis. So, this angle would be theta as well. So, I will just draw that separately over here. This is theta, and this is d, and this is the path length difference that we want to find out. Okay. So, you can write an expression for this saying that okay, sin theta is going to be equal to PLD over the hypotenuse, which is d over here. Okay. So, PLD is nothing but d sin theta. Okay, the path length difference is d sin theta. So, I would now apply this to that constructive interference criteria, which says okay, phi 1 minus phi 2 has to be equal to 2 pi m, but as we saw in that other just a while ago, phi 1 minus phi 2 can be written as 2 pi over lambda multiplied by n multiplied by the path length difference, right, which we can write as d sin theta over here, that is equal to 2 pi m. Okay. Now, of course, we can go in and say okay, 2 pi and 2 pi cancels. So, if I wanted to find the angle at which the first maxima happens, okay. So, the angle at which the first, so in general I should write this as theta m, okay, because that corresponds to different orders having a different theta m. But if I look at the first for m equal to 1, and let us say we are observing all this in air, so n equal to 1 as well, then theta 1 is going to be given by sine inverse of m equal to 1 over here. So, you have lambda over d, correct? You understand what I have written here? This is the condition for the maxima, right. So, we are looking at the maxima, this is for the constructive interference criteria, 2 pi multiplied by m is the condition for constructive interference. Okay. So, now I can, I know the different values I have. So, let me just first say that I am actually doing this for the red color. So, this would be sine inverse of 0.65 into 10 power minus 6 divided by d, which is the distance between the two slits, the center of the two slits. So, that is 0.8 millimeters. So, 0.8 in 10 power minus 3, and this will work out to be approximately 0.8 milliradian, 0.8125 or something like that. Okay. But now from this I want to find out x1, right. So, x1 of r is nothing but I can write it as d, that is the distance between here, that d times tan of theta r, okay, because tan theta r is nothing but x1 over d. So, x1 I can write it as d times tan theta r, and theta r I know. So, I can substitute, and d I know, d is 1.5 meters, right. So, I can substitute both of those there, and what I get is 1.218 millimeter. Okay. So, the first maxima for the red color appears at a distance of 1.218 from the optical axis. Okay. Now, if I do the same thing for orange color, I get to find out theta 1 for orange, and theta 1 for orange is sine inverse of lambda over d, where lambda is 0.6 microns, right. So, if I substitute that, this one will work out to be roughly about 0.75 milliradians. If I substitute that in this expression, I get the position of the first maxima for orange color for a wavelength of 600 micron is given by 1.125 5 millimeter. Okay. So, the difference between those two, so x1 the position at which the red maxima happens, the position at which the orange maxima happens is now 93 micrometers. Okay. So, you see the maximum for the red happening at a slightly different location from the maximum of the orange. So, if you want to discriminate between these two, if you want to pick red and not orange, what would you do? Yeah, just put a pinhole, right? Just put a slit over there. Okay. If I put a slit over there, then I can actually see the red color from the orange color, right. So, what should be the width of the slit? That depends on the discrimination you want to get, but let us say you are okay with half of the orange coming into the red and so on. So, the slit width to discriminate the two is basically, if you say half of that you put as a slit width, this is corresponding to 46.5 microns, then you get predominantly red or predominantly orange depending upon moving that slit. And of course, like I said in the previous case, today if you want to do that, you forget about the slit, you put a CCD array once again, okay. And the CCD array is typically the pixel spacing is less than 10 microns, okay. So, you say, okay, this pixel is picking up red predominantly, and you move away almost 10 pixels away, you are picking up orange. But essentially what we are seeing here is that whenever we talk about interference of light, that interference is actually wavelength based. Okay. So, you can use that interferometer as what? Spectrometer. A spectrometer, what does it do? It just gives you what is the intensity at different colors. Okay. So, because this this interference phenomena actually depends on wavelength, you can use that as a nice way of picking out different colors. So, we saw some other thing in ray optics where with a simple prism you can actually get all these colors separated out, you can pick out these colors, but that is based on what is called material dispersion, because the material responds in a different way for different colors. But here there is no material involved, it is just a structure that you have that provides interference, and that interference, wherever you see interference, you see that there is, it is actually dependent on the color, and that actually gives you an opportunity to discriminate between different colors. Okay. So, that just a quick example of some of the concepts that we learned so far. There are more tutorial problems, and so I would encourage you to go back and try to solve all the other problems as well. Okay. So, with that, let me stop this session. Thank you.